and welcome to the 15th edition of ChemPlus 2022. And we are currently hosting the first day of ChemPlus and the second plenary lecture. And our guest speaker is Dr. Swapna Singh from IIT Madras. She's a newly joined assistant professor. And I'll give a short bio of her. Dr. Swapna Singha Rabha is an assistant professor in the Department of Chemical Engineering at IIT Madras. Her research interests are CO2 capture and sequestration and process intensification of multiple reactors. She did her PhD from IIT Delhi and postdoctoral research at Helmholtz-Zentrum Dresden-Rossendorf, Germany, National Energy Technology Laboratory, Morgantown, USA, and Imperial College London, United Kingdom, before joining IIT Madras in 2021. Her current title for the plenary lecture today is Tackling CO2 Emissions from Industry. We're all very excited to hear your lecture from you today.
Thank you, Mani, for the introduction, and thank you for also inviting me to speak in front of you all, because as Mani said, I recently joined IIT Madras, and I haven't got the opportunity to meet you all in person. So it's a good opportunity for me to interact with all of you. Yeah, thank you. And I'll share my slides now. Can you see my slides?
Yes.
Yes. Okay, so I'll put this here. So I will, today I'm going to talk about tackling of CO2 emission. Like now, I think CO2 capture, utilization, and storage, it's kind of a hot topic now. So all the world, everywhere, they are discussing about it, how we can reduce. Maybe you heard the term about zero emission, zero CO2, net zero, like negative CO2 emission, all this term you might have heard about it. So today I will explain, like, why there is a need today to do this, and what are the technology to do this, and how we can progress forward, and what is our role in this. So I'm gonna talk briefly about the three aspects of it, like carbon capture, utilization, and also CO2 storage. Like mainly focusing since I'm a chemical engineer, and it's like a chemical engineering seminar. So I will mainly from how to tackle CO2 emission from the industry. Okay, so I'll start. So now why we need to tackle CO2 emission, why it's a big deal. So now, for example, now if you see, a minute. So now this global energy, if you see this graph, global energy CO2 emission, which is again, I have taken from International Energy Agency report, which is on special reports on carbon capture, utilization, and storage, where you can see the global energy, or the global the CO2 global CO2 emission increases day by day because of the increasing industrialization, increasing globalization, where people travel from one, air travels are increases, transport is increases. So global energy, with the development of the countries, the energy CO2 emission is also increasing. You can see in 2020, there is a dip, which is due to the pandemic. You can see there is a dip in the CO2 emission, because at that time the whole world is kind of pause. So there is a dip. But again, in 2020, it is growing up, because we need energy demands are more. Like we need energy in everywhere for electricity. Now, for example, we need to do these conferences online, we need to have this energy, light, current, to charge our mobile phone, which is kind of our, we cannot live without it. So we have to charge it. So we need energy. And how this energy is coming from? So from fossil fuel or power plant, those type of industry. But what's happening with this, and because of that, CO2 emission is also increasing. Now the CO2 emission, increase of CO2 concentration increases in the atmosphere, which means this climate change. So from international intergovernmental panel of climate change, where IPCC, it's kind of a lot of countries together, a lot of government together, they talk about like it's a panel on climate change. They say that like scientific evidence for warming of climate change is unequivocal, means it's a fact, it's not a lie. So some of the evidence which is some of the evidence of climate change, you can see that global temperature rise. For example, in the last few years, global temperature is rises immensely. You can with the fact or the reports or tally the number says that the last 7 years are the most hottest year in last 40 years, and 2016 and 2020 is the hottest year in the like a record. So which means something is happening, like the temperature global warming is happening. That's why its temperature is rising. Another example is the shrinking, the ice is melting. For example, you in the report or the news, you must have heard about how about Greenland and Iceland, like Antarctic ice has been decreasing the ice level. Some of the numbers are that, for example, the Greenland lost at around 279 billion tons of ice per year from 2093 to 1919. So there is something happening. And same with level, like ocean, for example, here, the ocean water temperature is also rising. The first layer, the top layer ocean is now, it's like a 33 degrees centigrade, it's a rise. So it's a quite a bit rise, which also affected the declining aquatic sea life. So there is less sea, and also one of the extreme events, one of the evident of the global warming is extreme events, which I think all of us, I think, encounter or experience in the last couple of days. Even in the last year, we had lot of floods are happening, lot of cyclones are happening all over the world, a lot of extreme events we all encounter. So these are the evidence of climate change, and which is why happening because the CO2 emission, the global, the layer of CO2 around the earth is increasing. The temperature is increasing, and that's why all this climate change is happening. So we have to do something. We cannot leave it like that. Like we cannot keep the CO2 emission to increases. We have to do some actions to reduce the CO2 emissions so that we can live. We means also human being, also everything can live peacefully or without means extreme events and all. So what are we doing? So there are some key the government, for example, IPCC has a lot of taken an initiative. Some of the key milestone of IPCC I'm mentioning here. The first step towards is achieving global emission reduction. First, we have to reduce the global emission from the industry, from the industrial countries, is first discussed at Kyoto Protocol in 1997, where a few of the countries has signed the Kyoto Protocol to reduce the CO2 emission from their country. But that time, many of the countries hasn't signed. Even US didn't sign. But that is the first step towards reducing CO2 emission. The next step is in Switzerland. It's Bern, where IPCC report state bluntly that there is a global warming, and it's unprecedented since the end of the last ice age. So that was the observation. It was the study from MIT. So they have presented there that global warming is happening, and we have to do something. The turning point of for the climate change is coming at the Paris Agreement, which is 1915, where almost all the country realizes in between 2020, 2001 and 2015, a lot of IPC has been many countries come together, but finally the turning point come when the Paris Agreement was signed, and then all the countries are aimed to limit the global warming to less than 2 degrees centigrade. Then what is the level of 1990? So and in between that also 2015 to 2000 till now, the lot of the reduction, for example, lot of claim or lot of aim has been put, for example, Europe has like they promise that they can go to net zero by 2030, and many countries has given a number. So for India's turning point recently, it's happened in COP26, where in Glasgow, where the climate and this conference happened, where the India promised or pledged to reduce the total projected CO2 emission by 1 billion tons from now to 2020. So it was a promise to reduce the CO2 ton by 1 million tons. The reason there are a lot of initiatives taken on the renewable things, and also to achieve the target of net zero emission by 2070. So this is the turning point of India and what's happening now. What is the status of this climate change policies? Now, from where is CO2 emission coming from? So now this is a CO2 emission in 2020, which is after like 2021, where all the most of it's a global CO2 emission in the most recent. Till some of the already carbon capture work has been already initiated, already developed. Still, you can see there are a huge CO2 emission, which is because electricity and heat, the source of CO2 emission is most by it's coming from electricity in heat, which means that most of our CO2 power or electricity and heat is coming from fossil fuel power plants, for example, coal, natural gas. So it's just we are still, our energy industry or our power industry is still dependent on the fossil fuel. And next is the industry, chemical industry. Our a lot of the household stuff and a lot of chemicals are coming from the chemical industry, which is also a source of CO2 emission. Then next comes the transport, cars, vehicles. Those are just because of the transported CO2 emission, which is the second highest. And also it's coming from building industry. Building industry means to build the cement industry, steel industry, aluminum industry. Those are the industry it's coming. So most of the, from here you can see that the majority of the CO2 emission is coming from electricity in the industry. Now we have to see how which industry, if you plot it like this, is again a plot from this IPCC report, where you can see most of the power is coming from the coal. CO2 emission coming from the coal means that we are still dependent on, our power industry is still dependent on the coal and natural gas. So now to reduce the CO2 emission, we cannot just remove this industry. We cannot take a decision like, okay, we'll stop all the fossil fuel industry or coal industry or coal power plants or steel industry, cement industry. We can close everything. We'll go totally into renewable energy where CO2 emission will be less, and we cannot do at this moment right now because our demand is very high, and those renewable energy, the power coming from solar and wind, hydro energy, it's not sufficient to fulfill our demand, our energy demand. So we still have to depend on this fossil fuel power industry and also this CO2 emission based industry, for example, steel, carbon, because we need to also have infrastructure, right? So we cannot just remove this industry from our life right now. So what is the solution? So one of the solution is CCUS, the air cum reverse. Now the CO2, the importance of CO2 carbon capture, utilization, and storage, that it will make a sustainable development scenario where we can secure sustainable and affordable power system. How we can do it? That's with the help of CCUS, we can retrofit the existing CO2 existing power industry to reduce the CO2 emission without drastically changing the dependency on the existing power plant. So we have to rectify those industry to capture the CO2, and also it will be utilized or it will be stored somehow to reduce the CO2, rectify in a way that it will reduce the CO2 emission, but without disturbing the existing power plant industry, because we need the energy and demand, because everything is dependent on energy now. So that's how the CCUS come, which is nothing but CO2 capture, utilization, and storage. Now, next is what is the capture, utilization, and storage. As the name says, first is like a CO2 capture. There is two different ways of capture: direct capture from air. Another is, which is related to industry, point source industry. We capture the CO2 at the point when it is coming from the industry directly from the fuel gas. We capture at that point, and then the captured CO2 is transported, and then either it will sequestrate into the deep ocean, where in the form of hydride, solid hydride, CO2 hydride, or it can be used in enhanced oil recovery. Like in enhanced oil recovery, for example, you inject it, with the help of CO2, you can enhance the oil. One side you can push CO2 with water, and then which dilutes with the oil, and it helps reduces the viscosity of the oil, and it helps to move faster the oil. So that is one of the sequestration process. Another is when we can store the CO2 in a reservoir rocks, in the rocks, where the CO2 stays there for 100 years, more than 100 years. So these are sequestration process. Another is utilization, which is another important application, like, where CO2 transport, the CO2 captured from CO2 point sources or direct sources will be utilized for further value-added product, for example, for cement production, for some chemical productions. So this is CCUS, where it's like the first is the capture, then it was transported and utilized, or it was sequestered to some store somewhere. So this is CCUS means this is. So now I will tell you about what is the different technologies for CO2 capture. I'll go step by step. First is the different technologies of CO2 captures are first. It's that there are three different technology. This is, I'm talking about the point source, which is based on the industry, where we can capture the CO2 from the industry. One is post combustion, which is means that the CO2 is captured after the combustion happened. Means that fuel and air, it was put in the boiler, and then react, the steam generate, which is sent to the steam turbine, and power is generated. But the fuel gas, which is out from the fuel gas, which contains a lot of nitrogen and CO2, then it was captured with the help of different options and technology, and then CO2 is separated from the nitrogen, and and CO2 is transported. Another process is pre-combustion. We did the CO2 capture before the combustion happened. So, like for example, from the gasifier, syngas is forming, which is hydrogen from CO2. Then CO2 is captured, then only hydrogen remain. Hydrogen goes to the combustion turbine, and then the output at the output we don't have CO2 emission. So it's called pre-combustion. Another is Another is in oxy-combustion. In oxy-combustion, what happened? The combustion is happening with oxygen. For example, nitrogen, with the air, you have oxygen and nitrogen, right? So nitrogen is separated because in the fuel gas, you have nitrogen and carbon dioxide. So CO2 capture process become more tricky with fuel gas when nitrogen is present, because there is also NOx can also form. So we have to separate in a different way. In oxy-combustion, what happened? The nitrogen is separated before it goes for the combustion. So combustion is happening only with the help of oxygen. Then the CO2 is forming. The advantages of oxy-combustion is that the system is a bit complicacy of separation of CO2 from the we don't have to exactly separate here separation, because the output and the output gas is the CO2. We don't have to separate from nitrogen to CO2. However, the post-combustion is like before combustion. It's more commonly used in the industry because there is a chance like retrofitting. You get the combustion and you can retrofit the product after the combustion happened. So it's easier for the retrofitting in the industry. So that's why post-combustion is most commonly used. Now, these are the different technology, how we can capture the CO2 in the industry before and after combustions and also oxy-combustion. Now, how we can capture, like, this is CO2 capture, how we can capture. Again, there are different routes. For example, we use absorption technology, or where CO2 is captured with a liquid solvent. For example, amine is one of the most common solutions or solvent is used, which is used for CO2 absorption, which is a kind of more mature technology right now, where a lot of industries has been used to absorb the CO2 from using the liquid-based solvent. And then another technology is membrane technology, which is, it's not commercially applied yet, but it is still in the lab scale investigation, is lab scale. For example, some inorganic membrane, polymeric membrane, also some mixed matrix membrane, which is, again, it's a lot of thing is and developing, like a lot of membrane material is been developing, and has been a lot of work is going on the lab scale. Another route is adsorption, where adsorption means that a solid sorbent material are used in the system, where CO2 is absorbed in this solid material, and then again you can regenerate the sorbent material, and you will get the CO2 out from the sorbent material. For example, zeolite, carbon-based, and also there is metal organic from metal oxide, and also this supported ammonia. This technology has been also, it's very attractive right now because of because you can regenerate the sorbent solid materials quickly compared to amine based, because regeneration from a liquid, separating the CO2 from an amine solution, it's a bit difficult than separating from the solid. So, but still currently it is not in a large application industrial scale, and there is also a chemical looping system for CO2 rate, where it's kind of second generation of the oxy-combustion system, where two different, one is fuel oxidizer is used and one is air reducer is used, which is called carbon looping technologies, which is also commercially not implemented here yet, but there are a lot of pilot plant work demonstration has been working on the chemical looping system. Now, what are the main challenges or R&D required for this system? For example, sorbent, which is the absorbent system, which is a mature technology. These are the amine scrubbing using methyl amine. But the important challenges is the cost, high energy cost for solvent regeneration, as I mentioned it before. And also because it's a liquid, it's just by evaporation, most of the solvent loss is also happening. And then because of the corrosive nature of the liquid, the equipment may corrode it, and formation of cryogenic nitroamine is also one of the challenges. Main important R&D needed in the systems are advanced solvent material, which can be generated with less energy, advanced process intensification, how we can intensify the process, and also the method to mitigate the aerosol formation and also the corrosion, and also heat control is another R&D area which needs to be done for solvent-based absorption system. And another is sorbent-based system carbon capture technology, which is called adsorbent. You can AB, and here it's AD, where the advantages is low sorbent regeneration cost and immunity to the moisture effect. So you don't have to remove the moisture before this absorption CO2 capture process. Important challenges is technology is less developed compared to this absorption process. Heat control is a bit difficult, and also stability and attrition is a problem. R&D required is the advanced the solvent. A lot of development is going on and developing new solvent materials, and also process intensification, and also the new reactor design. Another is membrane. Important challenges is the partial pressure of CO2 is very low in the fuel gases, and is R&D required for a lot durable, low cost durable membrane, and advanced for intensification, and also configuration, and how we can use this in a larger scale up. So these are the few challenges and R&D for different technologies of CO2 capture. However, some work is been going on all over the world, and also there is initiative also in the CO2 capture at IIT with absorbent material, and also with the help of CFD, and also the absorbent system has been going on, and main target is to look at different, so also at the particle size or material characteristics of that scale and to the lab scale, and finally main aim to the pilot to study a pilot scale, and then main aim is to technology transfer to a industrial scale. So this is the initiative of carbon capture at IIT Madras. And then now I again go back to the utilization part and sequestration part. This is till the carbon capture part, how we can capture the CO2 from the point source from the industry, and now next how we can utilize it, or how we can store it. If we get the CO2 somehow like with different technology, now what to do with it. So one of the a best option is that if we can utilize that CO2 to produce some value added product. Like if you use this CO2 which is captured from the industry, then you can use it to produce the advanced materials, fine chemicals, intermediate chemical, or some base chemicals with the help of thermochemical conversion or photocatalytic conversion. So it's the best solution. However, the challenge is that a lot of energy is required to transfer CO2 into useful chemical. And this energy, from where it is coming out, again, it is coming out from the CO2 emission technologies. So we have to see how this energy, whatever you are using, is it we have to do how much CO2 to utilize the CO2, how much CO2 is again emitted. So we have to figure it out, what is the balance, and what is the product, and what is the market value of the product. Based on that, CO2 utilization has been we have to work on CO2 utilization, and a lot of work has been going on also to work on the CO2 value added product using CO2. So another technology, like what happened to the captured CO2, another way is to sequestrate, to store. There is also different ways to store CO2. One of the way to store CO2 is geological carbon storage. So most of you may be surprised, where if it's underneath the earth, if we store CO2, is it safe, or is it coming out? Those are the things I think a lot of people might have are you feeling safe if we inject the CO2 underneath your house or something like that? It's a lot of people has this curiosity, but usually CO2 storage happen in in mountains where underneath many kilometer underneath the main the ground underneath, for example 2 kilometer underneath earth. So it was stored. So it's a process to store the CO2 in the subsurfaces safely and prevent it to re-entering into the atmosphere. So storage in the deeply oil and gas field and deep saline rock formation, it's a part of enhanced oil recovery, and it is also stored in shale and basalt. If you say this, our earth is also a very, I would say it's a porous material, and it's a very layered material. So we have to choose a storage site where we can store the CO2 so that it cannot come out. If you see, our earth is like a different layer. We have to choose a site so that CO2, it should be porous enough, or permeability should be good so that it can flow into that rock, and also it should be covered with the cap rock. Cap rock means that it's like a storage site should be also like where your CO2 stored, it should be covered with a cap rock, means that the permeability or porosity is zero, means the CO2 cannot pass through the CO2. And also the CO2, when it's stored, it reacts with the minerals present in the rocks, and it's stored there. It becomes a solid minerals, and it stays for 100 years. So Geological CO2 storage is a proven technology. It is reported by International Association of Oil and Gas producers that geological storage is a proven technology necessary to achieve climate neutrality. In Europe, it's like Europe-based to for a cost-effective manner and to enable the negative emission. So if you're thinking this is like a not safe kind of, it's already a proven technology. It's already happening in Norway, US, and also in Europe. So in India, the awareness and also the it's not yet fully it's applied the geological carbon storage, but there are a lot of initiative has taken by the government in India to work in this field also. So the key questions are, will CO2 leak back to the surface? This is one of the important questions. And will CO2 storage create unacceptable environmental hazard? These are the questions. And is the storage capacity is enough? These are the key questions. And for that, we have to analyze this site, analyze this rock first, like key requirement to characterize and select those site where we can store the CO2. So this is again a research, like we have to first explore site characterization, selection and performance prediction, which is the key for the successful geological storage, because there are a lot of key process governing the how we can trap the CO2. I won't explain it here, but there are different steps also, like, you know, it's not the only storing, but a lot of thing is happening when CO2 is injected into the this porous rocks or reservoir rocks. So these are some of my results. You can say, means I would like to show you this is a reservoir. It's a solute transport in a reservoir rock. How you can see how the solid is transported in a reservoir rock. It's an experimental work, and this is a simulation rock. So it depends on that. Then from this work, experiment and also the simulation work, you can find out the transport parameters. What will be the residence time? What will be the permeability of the rock? What will be the transport and mixing process? What are the transport parameters is required? And this will help to design a field study where, like, you know, where actually you can store the CO2 in a plant. This work is solute. It's a cation. It's a carbonate rock. It's a cation carbonate rock. It was also taken from the reservoir site, and the reservoir site it's in the Switzerland, and so it was successfully the CO2. It's a success CO2 stored in the Switzerland mountains. So this is one of the work of petrophysics studies for the site characterization. So another options for CO2 capture, CO2 storage are the CO2 storage in ocean. Like you can inject CO2 into the deep water, and it will dissolve into the water, into the liquid. Then and it can convert the CO2 into biocarbonate. Also, there is another form of storing CO2 it's in the deep underneath the sea in the form of hydrate. Means in the form of CO2 is the gas formed at high pressure, and at very low temperature it becomes like a solid hydrate. So this is also one way to store CO2 underneath the sea. And there is some another interesting, very interesting, and the CO2 storage are like CO2 storage in kelps, like for example, seaweed kind of ocean leaves, seaweed or kelps, which is also used for CO2 storage. Kelps sequestration of CO2 in Australia. There are a lot of work has been going in Australia with near the sea, because this like kelp is available in near the sea, right? So you can get the sea, or you can invest also to some bioreactor to grow the kelps, which is like a seaweed, which can also use to, which is like a photosynthesis is happening there, which store the CO2. And the most, I think it's the most different, everybody know deforestation, we should grow more trees so that it absorbs more CO2. So these are different techniques for CO2 storage. For one is geological CO2 storage, another is in the ocean, and also enhance oil recovery with the help of CO2 is another way to store CO2, and also the biological CO2 storage. Now, So I explained what different types of like what is the carbon capture, utilization, and also storage. Now where we are now, what is the status now? If it's like, what's happens, these are the technology available. There are a lot of work has been going on with that, but what is the status now? Where is are we able to remove the CO2 or emit the CO2 from the like industrial CO2 emission, or reduce the CO2 emission from the industry? So these are again from the International Energy Association report, is that the facilities are already operating and development is going on from 2000. These are the report, like for example, in 2010 there are less operating, more early development and advanced development is going on. But as the years progresses, if you can say in 2020, there are the most of the operating the plants, CCU facilities are increasing. So there are more plants or more CCUS facilities are operating and operating as the year goes, and which is expected to increase more. And because there are a lot of, you can see the green early advanced development is going on, and also the under construction is also going on. So this is the map for world large scale CCUS facilities operating in the last few years. But significant improvement are needed. Again, a lot of improvement or a lot of research work are needed, and the support of government is needed to widespread deployment. Okay, and then what are the thing of focus for the technology improvement are the reduce cost. We have somehow, you can see this technology is expensive. Like you have to add one technology, like you are in the industry, you have to add retrofit one technology, and the solvent cost is more, solvent cost is more, and also this energy requirement is more. So we have to somehow find a way to reduce cost. And most of the industries are hesitant to initially put because it costs more, but now they have to do. I think it's kind of policy. So we have to focus on the technology improvement can be how to reduce the cost, reduce the energy demand, and if CO2 capture can be integrated with the utilization. If we can utilize a CO2 or use CO2 to produce some value-added product, then it will be very good. So these are the things which is technologies we need to focus on to support our widespread deployment of the CCU facilities in the world. Now, this is the status of the CCUS over the world. Now, this is what's happening in India. What is the status of CCUS in India? If you can see, in India, not much has been work compared to other countries. There are not much has been done, but if you see the in India also, there are a lot of industries, right? But only CCUS as per the report in the CCUS facilities, it's also a global status. This map is also produced from this global status of CCES 2020. Only one, the CCUS plant has been reported in this map, Tuticorin Alkaline, which is from Tamil Nadu actually. Tuticorin Alkali Chemical Fertilizer Limited has been this is the first industrial scale plant for carbon capture and utilization in India, which capacity is 164 tons per day. But there are some other also urea-based company, which is where end product is being used for producing fertilizer, is also there in India. For example, in Uttar Pradesh, in Odisha, you can also in Tata Steel also recently built a CCUS plant for the boiler for the boiler unit using amine solvent. So this is the status of CCUS in India, which is less, but we are still working, and due to the initiative taken into 2021, so there are now I think we will move more faster to implement CCU facilities in India to reduce the CO2 emission from the industry. So now, how we can be successful for energy transition? As I said, is that we cannot, like industry cannot do it alone, or academic, like we are also academic people cannot do it alone. We need to, for a successful energy transition, you need to have a support from the government, because there are a lot of policies involved, like, the policies involved for CO2 capture, CO2 storage, and also utilization. So, and also industry plays a huge role, because they have to deploy the technology, or they have to build the technology industry. And also academia is also important, because see, this technology has to be developed. It cannot be developed in a large scale, right? We cannot just build the technology or reactor of carbon capture plant just to make, but we have to do a lot of research on it. There, how the academic institute role comes out, like we to look the future, look the future, for example, to 10 to 50 times ahead, from the small setup, small lab scale state, pilot state. That research, I think academic institute plays an important role to find out the innovative solution or innovative technology for a new CO2 capture technology or storage technology, even for also for CO2 utilization technology. So our role is to look into the future, have a lot of policy and training can help also industry, and one of the important role of also academia to prepare young people like you to tackle this, to take this responsibility in the future direction, to invent more catalyst particle or more solvent material, advanced solvent material, which can be like a low cost, which can easily or also work on different renewable energy. So renewable energy sources, or some other, for example, CO2 utilization. So to prepare you guys to take this responsibility for the future direction to tackle this climate issue. As I said, this issue is serious and we have to do something about it. So this is it for today. This is my last slide, I guess. Yes. So yeah, with that, I would like to conclude my talk today, and I'll be happy to answer any of your questions. Yeah, thank you.
Thank you for the wonderful lecture, ma'am. We have a couple of questions here and also on the YouTube chat. I'll convey them to us.
Yes.
So, Govardhan asks, is there any chance of the stored CO2 leaking to the underground water storage?
Yeah, as I said, that there is a way to store CO2 underground the ocean, ocean water, you said, right? Go ahead.
Yeah, is there a chance that it can leak into underground water and contaminate it?
That's contaminate. There is, again, there are a lot of issues or safety issues. That's why we have to store the CO2 in a way, in a hydrate form, like in a solid form, so that contamination is less, right? So we have to store it in a way that it will be in a solid form. It will stay there, and we have also, it will be underneath the ocean. Also, there is you have to go very deep. So yeah, there is a chance to contaminate, but again, we have to find a solution, in the form of hydrate, or how we can safely store CO2. Yeah.
Okay. So, and Priya asks, which materials have zero porosity so that CO2 doesn't?
Okay, there is some material. As I said, this cap rocks. For example, we have to choose cap rocks. They are not at all flow fluid will not pass through it. So, but cap rocks are, it's kind of zero permeability. There is no gas pass through it. So this cap rocks, which is I am talking about, which is used for geological CO2 sequestration, which is again in the subsurfaces, where it's a kind of rock which is completely impermeable in nature, and porosity is very less and unconnected porosity, so the gas cannot pass through it. Yeah.
And Jyoti asks, pH reduction in ocean due to. Okay, Jyoti asks, does pH reduce in ocean due to more of H plus ions? How can it be neutralized?
I think it's the pH is not changing because you also it does, it's not that CO2 directly into it. It has to go through pipeline and a lot of things, like you have to go in a ship and a lot of pipeline has been used. So and then it was stored. There was a bit connection disturbance in the net connection. Can you hear me,
Yes,
Manichandra?
I can hear you now. Yes.
Yeah, okay.
Okay. Sorry for that on my end.
Yeah, it's okay. Even yeah, network connection is.
And Soumya asks, what happens to the stored CO2 underground over time for
Yeah.
certain years ahead?
Certain years ahead, the CO2 also react with the minerals present in carbonate. There are a lot of minerals also present in the rock. It react with the minerals and it stays there as a solid form in like for 100 years. So it's like, it stays there. But and there is like if earthquake and something comes, it might get like fracture, right? It might be then there is a chance to for a leakage of those things, that those are again the prevention has to be taken. That's why a lot of also work is going on. What happened if there is a fracture, for example, like earthquake, if there is a something shear, or if for even for the when you enhance oil recovery, when you inject or pump the CO2 with the change of pressure and temperature, if there is a fracture occur, what will happen? So there are also a lot of work has been going on or research has been going on to develop the fracture. But there is also one thing, we have to select those sites so that there is a like those materials don't like they heal. For example, they fracture and then they heal himself, right? For example, if there is a water after some time, those fracture is uh, which can sustain high pressure, the change of pressure and temperature, and plus also they healed by themselves. So yeah, those are the things, a lot of research, and that's why site characterization and this sample characterization, those are very important before you inject the CO2 into it.
So I think appropriate research is done before the site is selected.
Yes, that's very important. Yeah.
So the question is, so what challenges does India have to increase the carbon storage?
Yeah, so there are a lot of challenges. First, I think, for example, awareness. We still in I think in the we are still talking about like CO2 capture, CO2 storage, utilization. This CCUS term in the like institute. We are like talking at the institute, educational institute, or in the industry. But general awareness, general public is still not that aware of these things. So first, I think we and now since the government taking a huge initiative, huge step, so there is a kind of awareness because like all the industries has to do something to reduce the CO2 emission, and also for the public they have to also accept the fact that even for the CO2 storage, if you find a CO2 storage site which is safe, they have to also believe that it's safe. We have to somehow convince them it's safe, don't worry, kind of thing. And for also so CO2 for utilization and a lot of investment, the government has to do a lot of investment, also company has to do a lot of investment, but initiative has been taken, and everybody is moving forward or looking forward, like putting their effort, academia and industry and also government. So hopefully we can reach that. Yeah.
So we seem to be very hopeful about meeting the targets, but have we actually overestimated, or are these realizable targets?
This you say 2017 net zero, is it
Yes.
realized? Yeah.
Yes.
So I think, yeah, I mean, it's I think yes, because I think, for example, Norway, it's almost net zero. They claim to be by 2030. They are almost, they are like, they can maybe the deadline can be preponed. They has been started working way long back than India. I think they started in 2008 or 2000, but they are almost, they are claiming that they are almost going net zero, and it's before their deadline. So there is means that it is possible. But again, we have to compare to Norway and India. India is a huge population is huge, and also so we don't have, so that it's a challenge again. So, but if there is a target, so if everybody work towards the target, then it is doable. But how we can approach that's the issue. But everybody is hopeful. Let's see what happens. Yeah.
It's good to be optimistic.
Yes.
And so, with respect to utilization, what other ways can CO2 be utilized? Is there any chance of it being used as a fuel?
Yes,
or is it only an emission from a fuel?
No, CO2 can be, as I said, a lot of industries, like, for example, CO2 can be used as in fertilizers. For this in the fertilizer industry, that's end product can be used as a fertilizer, and also some value-added, also formic acid. There are some way to produce this value-added product, but again, the emission of the energy required for CO2, which also coming from, we have to see, it should not be, the emission is to produce that value-added product. We should not use more emit more CO2. So yeah, it's, again, there are a lot of discussion on it, CO2U and CO2 CCS and CCU utilization and storage. But I would say, according to me, according to my whatever my experience and also studies, I think it would be the good solution, or the a perfect solution, optimal solution will be to go together, CC utilization, because you cannot utilize all this. The CO2 emission is a huge number, right? So you cannot utilize all the CO2. So it would be perfect if you can utilize some of the CO2 to a value-added product and some CO2 to store. So that will be a perfect solution if we can go CCU and CCS together, then that will be an optimal solution.
I think that's the way forward.
Yeah.
And so we don't have any more questions, and we have reached the end of our lecture.
Okay.
Yes. And yes, actually, thank you very much for actually delivering such a comprehensive lecture, and also highlighting the responsibility that we as students have.
Yes.
Yes. And also motivating some of our audience to actually pursue research in this area. And so I, Manichandra, the president of AICHE student chapter, on behalf of just thank you for delivering this amazing lecture.
Yeah, thank you, Manichandra, and thank you all for listening to my talk. Thank you. Bye.
Good evening. Bye.